meeting. Preparing to live stream the meeting.
I see.
Okay, hello everybody, let's get started. So it's now 8. So welcome everyone to today's October Astronomy on Tap event here with Astronomy on Tap Gothenburg. So today we've got 2 speakers for you talking about different types of telescopes. So we have Miriam, who's going to be talking to you about the eROSITA X-ray telescope, and Alistair, who's going to talk to you about the Square Kilometre Array, or SKA, and that's a massive radio interferometer. So this is our online version of Astronomy on Tap Gothenburg. So hopefully with people from all over the world, but also here in Gothenburg as well. So we're here live on YouTube. We want to encourage all the people watching to ask loads of questions in the chat, and then we'll be able to select some of your questions from the talks to then go to the speakers after the talks are finished. But for now, please let us know where you're coming from all around the world, hopefully, and feel free to say hi in the chat. I see some people have already done so. So as always, we have 2 talks and then followed by a science quiz, which as always will have a quiz with themes based off the talks we have, just like we would do at our normal live events. And today the quiz will be at the end of the event after the 2 talks have finished. So please do stick around for that. So just a little bit more for any of our new watchers or new audience who aren't going to these events normally or haven't been to an Astronomy on Tap event before. This is a global network that we have of Astronomy on Tap. We're just coming to you from Astronomy on Tap Gothenburg. It started in 2013 and now there are 21 different groups in Europe and even more groups across the world. You can find out more about that at the website astronomyontap.org. So even if you're coming to us from elsewhere around the world, don't stop with this evening. Feel free to watch some of the other talks by some of the other groups around Europe and in America and the like. So who's here with you tonight? So I'm Holly Andrews. I'm here emceeing the event. So I'll be talking to you about who's going to be speaking to you and then relaying your questions to our speakers after their talks. We also have Andrea, who is helping out on Zoom, and she's actually streaming the event for us. We have Jan, who's going to be talking to you in the chat and getting hold of your questions for us. And we have Kiana and Paul, who wrote the quiz, and Kiana's going to be presenting it to you at the end of the event. And we also, of course, have Mariam, Alistair, who are our speakers, who have very kind of them, have volunteered to talk for you all tonight. And we also have several other members, Fran, Sandra, and Carmen, who also helped out putting this event together tonight. So thanks to everybody for helping out. So you can connect with us. Obviously, we're here on YouTube chatting to you tonight, but we also are active on our Facebook page. So if you have Facebook, feel free to like us on there. You'll get a lot of updates on there. And we also have a Twitter, so feel free to follow us on Twitter as well. And if you have any questions about tonight's event, or just in general want to get in contact with us and hear more about astronomy, we also have an email as listed here as well. But before speaking to our speakers or hearing from our speakers, we just wanted to present a bit of science news to everyone today. So today the Nobel Prize was announced in physics, and it came to 3 different people for astrophysics. So we actually have half of the Nobel Prize went to Sir Roger Penrose, and that was for the discovery that black hole formation is a robust prediction. Oh, sorry. Technical issues on my end. I will be with you in 1 moment. There you go. So hopefully that didn't affect the stream. So we have 3 winners for the Nobel Prize, one of which was Sir Roger Penrose, as I said, for his work on the theories surrounding black holes, but also Reinhard Genzel and Andrea Ghez for their observational work into looking at black holes as well, specifically into investigations around compact objects and the supermassive black hole at the center of our own galaxy. So do feel free to check that out on various news websites as well. Very exciting. And in fact, Andrea is only the 4th woman to win the Nobel Prize in physics. So personally, I'm quite excited about that one as well. So the plan for tonight, so we're going to hear from Miriam in a couple of minutes, talking to you all about the eROSITA telescope. So she'll give a 15-minute talk on that, and then there will be time for questions. This will then be followed by Alistair's talk on the Square Kilometre Array, or the SKA, again followed by a time for a Q&A. And then we will have a short break, which will then be followed by our quiz hosted by Kiana. So I hope you're all ready. Strap yourselves in. Feel free to go get a drink, either a beer, wine, or non-alcoholic. I'm here with some tea myself. So I hope you're all ready to enjoy tonight's evening. So I'm going to stop sharing this. I will now be handing you over to Miriam. So Miriam, when you're ready, feel free to share your screen and unmute yourself. Great.
Okay, I hope you can see it. Good. So thanks everyone in Gothenburg for the invite. It's a pleasure to me to talk about X-ray and the new brand eRosita telescope. And I hope you can learn something about these two topics in this short presentation. But before talking about X-ray, I need to tell you something about electromagnetic waves. And it's a concept that you live every day, you as a person. Why? Because electromagnetic waves are the ones that are coming out of your laptop to see actually this presentation. And we call this regime of the electromagnetic waves visible. So it's the light coming from the sun that you see with your eyes. When you're looking at the stars at night, that's the visible light. And it has a very short wave length. That's the reason that it's a wave and it has very short one. But if you want to see, for example, the craters of the moon, you need a telescope or binoculars. And then you can see more about, in more detail, what is in the moon. Or if you want to see the moons in Saturn, for example, you need to enhance your vision. But of course, if you want to go even further than the moon and the solar system, we need to construct bigger telescope to get these electromagnetic waves in the visible regime, like the one in the picture here. That is the so-called very large telescope located in Chile. But this visible light is not the only electromagnetic waves that you interact with in your daily life, but it's also radio. Radio are also electromagnetic waves, and the difference with the visible is that they have a longer length, from 1,000 to 100 meters. And the same, to observe the electromagnetic waves in the radio regime that comes from objects outside Earth, we need to construct radio telescopes like the one in Onsala, very nearby Gothenburg, that I'm sure some of you know. And how this telescope work, I will show you in a very sketchy way what is the basic principle for the optical and radio telescopes, how they work. So imagine we have a star that emit visible light and radio emission. And then imagine that this is a telescope. Yes, you can use your imagination, and that this is the first dish, the main dish. This is the secondary dish that is here. And we have our telescope. So the light is coming from a star or from another astronomical object in the radio or in the optical. It comes to the main dish, that is certain, it has certain shape, and gets reflected in the secondary mirror, and then you can see it. And that's basically how the optical and radio telescope work. Now, what about the X-ray? Well, the X-ray, in comparison with the radio and the visible light, has a very short length. It's the size of an atom. And the thing is, it's very energetic, and the waves are very energetic in comparison with the visible and the radio ones. And the good, for example, when you go for a doctor's appointment and you get an X-ray photography or your chest or the dentist or your teeth, the dentist or the doctor go outside the room because these rays, this X-ray can be harmful for you if you get a lot of radiation. Luckily for us on Earth, the atmosphere blocks this X-ray coming from outside, and we don't see it here. So that's a good thing. Unfortunately for the astronomers, that means that we have to send balloons or rockets, or even better, space telescope to observe this X-ray. And how these telescopes work? Well, imagine that we have now an astronomical object that emits an X-ray. And when it emits these rays, and it gets to a configuration similar to the one in the optical or in the radio, the rays penetrate, so we cannot observe them. we need a different configuration because they are very energetic. So the scientists came with a different idea on how to observe them. And this is how we do it in modern telescopes, X-ray telescopes. So basically we have like two plates, two mirrors, very in a way almost parallel to the rays that are coming from an astronomical object. They get deflected a second time, and then we can observe it, and that's very nice. And this was a mirror configuration proposed by a German physicist called Hans Volter. Now, how this looks in reality? Do we have 2 plates, 4 plates? Well, in reality, an X-ray telescope is basically a tube. And let me show you and illustrate a nice animation for that. In this one, you can see the cross section. You see the X-ray coming, and they will be reflected only with a certain angle. But now, if we want to collect as much X-ray as possible, we need a very big telescope. But of course, we cannot construct a huge tube. That will be very expensive and even more expensive to send it out of space, outside Earth. So what the scientists came is to make a lot of mirrors in a nested way. Let me show you how this works. So imagine like an onion, so many layers. So all these mirrors are co-aligned and they can deflect the X-ray and then we can detect them. This is an animation that you just saw. And this is how it looks in reality. So you have a scientist there looking at the mirror that is basically a tube. Then you have many tubes together, co-aligned, that they will reflect the X-ray into the detector. Now, let me tell you about a very nice astronomical object that I really like a lot because they are my favorite ones. That is the cluster of galaxies. As the name says, cluster of galaxies is a bunch of galaxies that are basically together, confined in a certain region of space. They are interacting. And here you can see an optical image of such, of an example of a galaxy cluster. Every yellow point that you see here is not a star, it's a galaxy. And as you might know, galaxies are composed of billions of stars. So here you have many, many billions or billions of stars because each yellow point here is a galaxy. They are very massive. And when you look with an optical telescope, you see this kind of image, and then you see this that you say, okay, the rest that is black, it might be empty, or it is empty. That's it. That's everything the light in the visible regime that we can get. But when the scientists pointed an X-ray telescope to there, they found that all this purple emission that you can see in this image, the same galaxy cluster, is coming in X-ray. And they discovered that in galaxy clusters, the space between each of the galaxies is not empty. It's full of a very, very hot gas that is emitting in X-ray. And that's why astronomers use different kind of telescope, because we can study different components of the different astronomical objects. And we can learn about different physical processes. And as happened with clusters of galaxies, there are many other celestial objects that emit in X-ray. Now, let me tell you quickly about Rosetta telescope. That is the telescope that I work in the Max Planck Institute here in Germany. So Rosetta stands for Extended Broadband Survey with an Imaging Telescope Array. Very long name. It was built in a German-Russian collaboration and is carried on board the Russian Spectrum RG spacecraft. It was launched last year, so it's new. And in this animation, you can see that Rosetta consists of 7 X-ray telescopes, and each of them have 50 mirrors each. So you remember this onion-like shape of the X-ray telescope. So each of them have 54 mirrors. Now, this is a nice sketch of Rosetta. That's how we imagined before the launch. And this is how it looks in reality before it was launched. We have here Rosetta that in this is about 2.5 meters, 1.3 meters in diameter. This is the platform where it's sitting and is rotating and is helping us to point the telescope where we want. And this one is another Russian instrument on the same observatory. How it looks inside eRosita. Well, this is the 7 telescopes that we have, as I mentioned, and each of them have the 54 mirrors. And then you see the tubes that I was talking about. So we have here 54. And these are the cameras that are collecting the X-ray photon for us. You can think of these as cameras like the ones in your smartphone, but they are way more effective, way more sensitive. They are meant for X-ray, but the principle is more or less as the same as the one in your camera in your smartphone. Now, the main goal of eRosita is to map the whole sky and to generate a map in X-ray. And how can eRosita achieve this? Well, first of all, we have to send it out of Earth, and it was chosen a special location, and that I will show you in this animation. There are some the so-called Lagrange points where the force of the sun and the earth cancel each other, or is kind of an equilibrium point. And eRosita was sent to the so-called Lagrange 2 or L2, that is 1.5 million kilometers away from Earth. And we choose, or the scientists choose this one, this point in order to eRosita can be rotating together with Earth. And that's very nice because then we can communicate with eRosita every day. We can check that everything is going fine with the cameras, that is still alive. And how eRosita will map the whole sky? Well, basically eRosita is rotating all the time, as you can see in this animation. So it's collecting the X-ray, it's rotating and rotating and rotating all the time. Each of these great circles that you see here, it lasts for 4 hours, and it moves a little bit, and again scan the whole thing. It moves and scan, it moves, scan. So that means that we can generate a map of the whole sky in very short time. And actually, eRosita can generate the whole sky map in only 6 months. So that's what it makes eRosita very powerful and very important instrument for scientists. Here is how you go from scanning the whole sky into these kind of projections that you can see. This was the animation that we did before the launch. And now I will show you the first all sky map map that eRosita has produced, because it has been more than 6 months already scanning the sky. And this is how it looks. This is a very high resolution image. It's a false color image. The yellow, blue, and red are different energies, are photons mapped into there of different energies. Here we have 100,000 of sources. Some of them have been discovered before. Many of them are new for us, at least in X-ray. There are huge structures here that no one's seen before. And my colleagues are working on determining what is the reason of them, why they happen, why they are there in X-ray. And we have all kind of objects here. And this is just for you to have an idea of the whole sky in X-ray. If we do have a zoom, for example, in this structure here, this is a supernova remnant emitting an X-ray. It's basically a star that exploded and expelled all the material around it, and it's emitting an X-ray. We have another one here, and a very faint one in blue that I hope you can see in your display. This is one example. Another example of what we can see with the X-ray with eRosita is the Large Magellanic Cloud, that is one of the nearest galaxies to us, to our Milky Way galaxy. And this is the mission that is coming from the Large Magellanic Cloud. And then we can even zoom more and see all stars, the supernova remnants that are there. So with this, I want to trigger your curiosity to learn more about X-ray astronomy, about eRosita. If you go to the webpage of my home institute, you can find very nice, many more nice images of the X-ray sky that we have at Choir. So to finalize, just hope you could learn 3 main things with this talk. That is, we need a space telescope to collect X-ray light from astronomical objects because our atmosphere blocks the X-ray waves. That the X-ray telescopes, the modern ones, look different from the usual ones that you have in mind from optical and radio. And there is a new X-ray telescope we call eRosita that is making very nice all sky map, and it will continue discovering new things. So thanks a lot.
Thank you so much for a really good talk. We've got loads of questions, so I hope it's all right if I get started on asking you those. So our first question is actually from Andrew, and that says, how big is this one telescope where you've got all these onion layers, and how close together are those sort of nested layers of all those mirrors?
Oh, yeah. I think from here to here, I hope you can see the cursor.
Yeah.
Yes, is 1.3 meters, more or less. I don't remember exactly how was the diameter, might be like 50 centimeters here. And yeah, 50 centimeters, then you can imagine these 54 layers, they are very close together.
Yeah.
Yeah.
So our next question is from Anders Kal, and that says, maybe I missed something. Are the 7 telescopes combined together to make a bigger virtual telescope?
Oh, yes. Yeah, because, yeah, indeed. The 7 telescopes are basically looking at the same point in the sky. So not only the 50 mirrors in each telescope are combined, but also the 7 telescopes. It's the only way we have as an X-ray astronomers to increase the collective area. So yeah, not only putting more mirrors, but also putting more telescope in the same instrument.
Okay, great. So our next question is from Clary Carhill, and that says, fascinating talk. What is the expected lifespan of eRosita?
Yes, so we expect that eRosita will be scanning the sky, doing this all sky survey for 4 years. So meaning it will perform 8 all sky surveys. And then at the end, all of them will be combined and we'll have a super high resolution, a very nice all sky map in X-ray. And after that, eRosita, we expect that it will go for another 3.5 years, where we will, the institute will open, it will be open for proposals for astronomers all over the world where they want to point the telescope and then observe their favorite objects. So it's about 7.5 to 8 years.
Okay, great. Our next question is from Franz Kirsten, and that says, does eRosita have the time resolution to do transient searches?
Ooh, yeah, that's not my main, but yes.
Okay.
I have a lot of colleagues that are doing transients. Yeah.
Okay. And our next question is from Fred Sinderman, that says, how high is the orbit of eRosita?
Oh, is okay, I can, is in L2, in the Lagrange point 2, that is 1.5 million kilometers away from Earth.
Wow, okay.
So it is not like here, the Earth, so it's really far away.
Yeah. So then we've got a question from MCTP, which says, how much time or how many passages do you need to observe your clusters of galaxies with eRosita?
Well, to observe, depends how far are your galaxy clusters. If they are nearby, with only one passage is enough. And you will not have that many photons or X-ray light, but it will be enough. But if your galaxy cluster are really, really far away, then you need to point your telescope and to point it. We usually in X-ray astronomy, we don't talk about minutes, or we talk about basically hours, how many hours you will be pointed. If it's far away, it can go up to 10 hours, basically.
Well, and then we have another question from Franz, which says, with the 8 full sky maps, can you also do diff maps between the different epochs?
Oh yeah, definitely. And that's what, for example, my colleagues on doing transients, that's what they are always, nowadays, for example, we are in the second whole sky survey. So they are always comparing if there is a flare somewhere that it was not before. So yeah, they are comparing the things all the time, but we can also combine them, that's for sure.
Great. Thanks so much for answering all those questions. I think those are all the questions that we have so far. So to let everybody know, we're going to now take a quick 5-minute break. So if I bring this up. Yep, so we're going to take a quick 5-minute break, and then when we come back, stay tuned. We'll be hearing about the square kilometre array from Alistair. So feel free to go get a drink, etc. Speak to you all soon. So we're just back from the break and we're going to have a chat from Alistair now. But just before we do, we've had another question in the chat for Miriam. So Miriam, if you're happy to answer that one.
Yeah, sure, no problem.
Yep, so the question was just, what are the most bright, or what are the brightest X-ray sources that we see in the sky?
Yeah, if you look, I encourage the guy or the person who asked to look at the map on again, and you see a very bright white spot in the center, and that's the brightest. I think, oh man, that's outside my field, but I think it's called ESCO X1. But to be honest, I don't remember if it's a supernova, which I don't think it is. It might be something else, but it is called ESCO X1, and that's the brightest one.
Okay, cool. Thanks. So Alistair, if you're ready to share your screen, then we'll get started with your talk.
Okay. Okay, can you confirm that you can see and hear me, Holly?
I cannot see your screen, so.
Okay, give me 1 second here. I'll fix this slight technical problem. There we go. Sorry for ruining the magic, folks. Right.
Great. You can see your screen now. Awesome.
Great. Thank you very much then. So thanks, Holly, and all the organisers, and thank you to everybody who's watching in Gothenburg and indeed from further afield. So I have 15 minutes today to tell you about the Square Kilometre Array, which I believe is probably the biggest telescope that very few people know about. So in the next 15 minutes, I'll try to introduce, first of all, what the Square Kilometre Array actually is. I'll then answer what I think is a question that might be on many of your minds, which is, what is radio astronomy? Why do I care? And why are radio telescopes so big? I'll give you a very brief insight into some of the science we hope to do with the Square Kilometre Array. And then at the end, I will discuss some of the technological challenges in building an instrument the size and scope of the SKA. So let's begin at the beginning. Well, the Square Kilometre Array is one observatory, but it's actually two telescopes, two radio telescopes spread across two continents. We have, first of all, what we call SKA-1 Mid, which is a mid-frequency radio telescope, which is based mainly in South Africa. SKA-1 Mid will initially contain 200 dish antennas. These are sort of scaled up versions of the satellite dishes you may have on the side of your building to collect TV signals. Each of which is about 12 meters across. The total collecting area of these 200 dishes is equivalent to about 126 tennis courts. And then moving to Australia, we have SKA-1 Low, which is a low frequency radio telescope. Very different technology. So instead of having dishes, SKA Low has antennas, which are more like the old analog TV aerials that we used to have, but with much more sophisticated and much more sensitive electronics. And these two telescopes are both going to be managed from an SKA headquarters building, which is at Jodrell Observatory in the UK. So here's a little artist's conception of what SKA-1 Mid in South Africa will look like on the left. And you'll see, if you've got a good screen, you'll see a car in that image, which just gives you an idea of how big these antennas are. And there are hundreds of them stretching across a plane. And then on the right, SKA-1 Low, which, as I say, is this telescope that's made mainly of dipole antennas. Construction on the SKA will be taking place for most of the next decade. And the cost cap for the first phase of SKA is a cool 675 million euros. So it's a significant investment from the astronomical community. A telescope on this scale obviously could not be built by only one nation. The SKA organization actually has 15 member states. So there are several European countries, including Sweden, are members of the SKA organization. We also have Canada, China, India, New Zealand, and of course the host countries themselves, South Africa and Australia. In addition, there are several other African partner countries which are colored pink on this map, and they're all contributing technical expertise and construction expertise. And indeed, several of these countries in pink are candidates to host antennas for future SKA expansion. So when you add together all of the countries that are shaded light blue and pink on this map, This is actually 40% of the global population is represented by SKA membership. So that's the kind of key headline facts and figures on SKA. I'll now kind of take a bit of a step back and just discuss what is radio astronomy and why are radio telescopes so big. So as we heard from the previous speaker, as astronomers, we collect photons from all across the electromagnetic spectrum. We have visible light, which is highlighted on this little figure here. This is the stuff that your eyes are sensitive to. Your eyes can see violet, blue, green, yellow, and red light. If you move to the right, we're moving to shorter wavelength light, so ultraviolet and X-rays, which obviously Irazita will study. And any of you who have been unfortunate enough to break a bone might have had an X-ray image taken in hospital. If you move to the left of the visible light, we have infrared emission. This is the stuff that comes out of your TV remote when you're trying to change channel. And we also use it to study stars and galaxies in the universe. Microwave emission, some of you may have heated up your dinner this evening on a microwave device. That's just a form of electromagnetic radiation. And then right at the very left, we have radio waves, which are just very long wave electromagnetic radiation. And if we look at, for example, one galaxy, what it might look like in some of these different wave bands, you can see the X-ray emission really traces very hot gas, hot plasma around regions such as supermassive black holes, or even extreme star formation events can be seen in X-ray light. Then you've got ultraviolet, which traces the youngest, bluest, most massive stars. Optical light, which I think most people are quite familiar with, that's all these nice Hubble Space Telescope images that we have as desktop wallpapers. But then moving to longer wavelength, we have infrared light, which sees cooler stars, older stars, and thermal dust emission in galaxies. And then right on the very left, radio waves. And what is really obvious is that with each of these different kinds of telescopes, you see different kinds of stuff about the universe. And so if we want to understand how stars, galaxies, and planets formed and evolved, we really need to approach this problem with the full armory of telescopes at our disposal. So the SKA is a radio telescope. Why are radio telescopes so big? Well, this is another famous radio telescope. This is the Very Large Array, or the VLA, which is in New Mexico. If any of you have ever seen the movie Contact, the one with Jodie Foster, this is that telescope. And it consists of 27 antennas, each of which is 25 meters in diameter. So this is an absolutely huge instrument. Why do radio telescopes need to be so big? Well, there are two main reasons. The first is that emission from space, radio emission from space, is very faint. And in fact, as radio astronomers, we use a special unit to describe this, which we call the Jansky, which is 10 times 10 to the minus 26 joules per second per meter squared per hertz. Now, this is a very cumbersome unit. It's a bit of a mouthful, but I'll try to explain what that means in terms of something that we maybe have more experience with, how much energy actually is in one Jansky. Well, if you step outside into Gothenburg on a cold December afternoon, you might be unlucky enough that you get snowed upon. So one snowflake falling from Earth, snowflakes tend to form about 2 kilometers up in the atmosphere. They may weigh something like 20 micrograms. And so the potential energy of a snowflake, which is of course converted into kinetic energy as it falls, is equivalent to about 0.4 joules. So if one snowflake falls per second over 1 square meter, then the energy of that snowflake hitting you in the back of the head is something like 10 to the power 26 times more than the energy that we get from typical radio sources that we study with radio telescopes. And in fact, the energy in one falling snowflake is actually more than the total energy collected by all radio telescopes since 1938. So we really are studying very, very faint processes here, and we need to build very big radio telescopes simply to collect as many of the passing radio waves as possible. The second reason why radio telescopes are so big has to do with something called angular resolution. Now, this is just a fancy way of saying image sharpness. But in effect, if you study space, or indeed if you take any kind of image, you want a very sharp image. You want to be able to resolve and separate two objects which are close together. That's what high resolution means. So if we think about a nice optical image of a distant galaxy, this is a high resolution image. It means that we can see things clearly which are very close together on the sky. If we then look at a very low resolution image, we can only really separate things which are very far apart. This is a very blurry image. And there's a very simple relation that allows you to predict how sharp an image will be. The sharpness of an image is given by the wavelength of the radiation that you're looking at divided by the size of the telescope. So to make that seem a little less abstract, probably the most famous telescope that we all know is the Hubble Space Telescope, which it's a visible light telescope. It has a diameter of 2.4 meters. And in an area which is 0.2 degrees in size, it can see 40,000 galaxies. So if you imagine holding out a grain of sugar at arm's length, that's roughly the area of sky that this image corresponds to. And you can see tens of thousands of galaxies here. If you wanted to get an image of comparable sharpness in the radio, well, radio waves are typically 250,000 times bigger than visible light. So you would need a telescope 250,000 times bigger than Hubble, which is about that size. Now, there are many reasons I can think of why we would struggle to build a telescope the size of Sweden, but fortunately we don't have to. Clever people in the 1960s discovered that you can actually synthesize one big telescope by taking two smaller telescopes and placing them a large distance apart, and then connecting them via optical fiber and using clever computer techniques to combine the signals. So that explains we can effectively use arrays of smaller telescopes to simulate one big telescope. So that's the principle on which telescopes like the VLA operate. We can extend this to a continental scale with the European VLBI network, which includes telescopes in Sweden, Estonia, Poland, Germany, the Netherlands, and the UK. And this is what ultimately the SKA is the ultimate expression of this, this approach. So some of the science we can do with the SKA. SKA science effectively covers all categories of astronomy. In fact, it was recently summarized in a 2-volume book with 2,000 pages weighing 9 kilos. Be rest assured, I'm not going to go through this all in detail. I'm just going to pick some science topics that are of particular interest to me. So one thing that SKA can potentially do is it can shed light on fundamental physics. Our current best understanding of the universe comes from Einstein's work on general relativity. Einstein observed that space and time are actually just different manifestations of the same thing, something called space-time. And what we call gravity is just the result of space-time being bent in local shapes. So space-time exists. If you place something massive on it, you bend space-time, and therefore gravity exists. General relativity explains pretty much everything that Newton's physics can explain, plus a few things extra. It can explain things like why time progresses differently if you're on Earth compared with in space. And that's vital that we understand that in order for GPS to work. It also explains how beams of radio emission come from pulsars. Pulsars are the cores of dead stars, which spin potentially several hundred times per second, and they have a polar radio beam, and every time the star spins, that beam of radio emission goes round like a lighthouse. Well, SKA has the potential to test Einstein's theories of general relativity like never before. It is believed that if we have a gravitational wave source with a nearby pulsar, then we will be able to test general relativity by measuring the time of these radio pulses arriving at the observer. A second aspect of SKA science, something which is closer to my heart, is galaxy evolution. So if I told you I had a time machine at my disposal, you would say, no, you don't. If I said, no, really, I have a time machine at my disposal, you might think to call for the men in white coats and take a step back. But really, I do have a time machine at my disposal. And the cool thing is, so do you. If you go out and look up at the sky on a clear night, you see stars, you see galaxies potentially. And because light travels at finite speed, that means it takes light time to get from A to B. So light takes time to arrive from distant objects to you, an observer. So for example, if you find the W-shaped constellation Cassiopeia and look at this star here, that's a star that's 250 light years away. So the photons that you capture with your eye this evening were actually emitted by that star when the American Revolutionary War was happening. And if you then look at M31, the Andromeda galaxy, this is the most distant object you can see with the naked eye. Well, that's 2.5 million light years away. So the photons that you would receive from Andromeda tonight were actually emitted when Homo habilis was the most advanced life form on Earth. And of course, with telescopes, we can see even further into the universe's past, and SKA is the biggest radio telescope of them all, so it will see further into cosmic history than any other telescope, allowing us to study the ancestors of today's galaxies. And lastly, on the SKA science front, SKA will be a candidate for telling us if ET exists. So if we think about some of the processes on Earth that create radio waves, things like airport radar, citizens radio communications, your favorite radio DJ, microwaves for cooking food, telecommunication satellites, and even nuclear weapons tests. Well, if any of that is happening on any of the nearest 10,000 planets around the nearest 10,000 stars, SKA may detect it. So SKA may tell us, in fact, if we are alone in the universe. In the final part of my talk, I'll just highlight some of the technical challenges involved in building a telescope the scale of SKA. So this is the slide that always threatens to break my laptop because it's got 2 embedded videos. As I said, SKA is really 2 telescopes in one. So in Australia, we have 130,000 of these dipole antennas, which all need to be connected to a supercomputer. And in South Africa, we have 200 dish antennas, which also need to be connected to a supercomputer. So one respect in which this is a big challenge is just the sheer construction effort that is involved to produce these antennas. There are also huge data challenges. So SKA will produce 600 petabytes of data a year, and that's enough data to fill the average laptop, so say 700 gigabytes of a hard drive, in 0.1 seconds. So it's a huge computational challenge and a huge signal transport challenge just to get all that data to the computer. Some amazing facts and figures. SKA will use enough optical fiber cable to go around the Earth twice. That's quite a bit of optical fiber cable. There will be a supercomputer on each site in South Africa and in Australia, each of which will be as powerful as 100 million personal computers, or in other words, each computer will be as powerful as the fastest supercomputer on Earth as of 2019. And lastly, SKA is going to be so sensitive it can detect ET, 10 light years away. That means we have to go to extraordinary lengths to make sure that we're not just drowning out that signal by radio waves that are generated on Earth. So SKA is being built in very remote locations and with incredibly complicated filtering technology to filter out all these human-made radio signals. And finally, my last slide. One of the key respects in which Sweden is playing a leading role in SKA, so in the SKA-1 mid telescope, which is the one that's in South Africa, we need 200 receivers for 200 antennas. These receivers need to be very sensitive, they need to be reliable, they need to work without any supervision, and they need to be producible quickly and to scale for 200 antennas. And Swedish academia and Swedish industry are actually leading the design and rollout of what we call the band 1 receivers for SKA mid. So a radio telescope can change channel just like you can change TV channel. And SKA-1 mid, one of its channels is called band 1, and Sweden is really leading the development of the receivers on that frequency channel. So I'll close just with a 1-slide summary. So SKA is an intercontinental observatory made up of 2 enormous radio telescopes. It will see farther into the universe and survey the radio sky 60 times faster than any other radio telescope on the planet. It will produce data at an enormous rate that even exceeds global internet traffic as of a few years ago. It's being designed, operated and funded by 15 nations who represent 40% of the global population. So it's a very inclusive project. And Swedish academia and Swedish industry are crucially involved at all stages of the project. So I will be happy to stop there and take any questions. Thank you very much.
Great, thank you so much for a very informative talk, really like telling us a good summary of what the SKA can do and how it's going to revolutionize looking at the radio sky. So we have a few different questions for you. So I think this one was covered a little bit in your slides, but our first question is from Fred Sunderman, and it says, how many radio telescopes and antennae make up each array?
So one thing that I was slightly sneaky about in my talk, so what I showed was for what we call SKA-1. So this is the preliminary phase of SKA, which will be built over the next decade. So SKA-1 contains in South Africa 200 large dishes, which are collecting mid-frequency radio emission. These are the big 12-meter antennas. And in Australia, 130,000 of the sort of TV aerial style dipole antennas. That's SKA-1. but the full SKA, which is what will be an add-on to SKA1 over the 2030s, that will contain something like 1,000 of the big antennas and several 100,000 of the dipole antennas. So the name of the telescope derived from the fact that when it's fully constructed, it will be equivalent in collecting area to 1 kilometer by 1 kilometer of sheer metal. So it's a big, big project.
Yeah. So our next question is from Anders Karl, and that says, is there an optimal distribution of the antennas? They said the low frequency SKA looked randomly distributed when you showed it, but as I'm sure they've got a thought process behind it. So
the thought process is actually basically the random distribution works as well as any more complicated array geometry. So one of the ways in which we improve the quality of radio images is to effectively keep the shutter open for a very long time. So you might take a 10-hour observation, and as that 10-hour observation progresses, the Earth is, of course, going from night to day. So the Earth is rotating. That means the telescope orientation is changing with respect to the source. And as it does that, the image quality improves. Now, if we built an array which was on some kind of symmetry, so for example, the VLA in New Mexico, it's kind of shaped like a Mercedes-Benz badge. So there's a northern arm and then 2 arms of antennas that come out in this way. That actually doesn't give you an optimal imaging capability. It turns out that distributing the antennas more or less randomly actually produces better images. The main constraints on where the antennas are is that they want to build them in locations that are very radio quiet, so far away from human civilization if possible.
Okay, so our next question is from Kiana, and that says, do you know if Sweden is going to be physically constructing the development of the band 1 receivers? If so, how are they transported to South Africa, if you know?
I believe Sweden is involved in constructing them. Certainly Sweden built the prototype of their band 1 receiver, and it is currently in South Africa on one of the SKA prototype dishes. And so that was designed by Chalmers University of Technology and Onsala Space Observatory, and Swedish industry was involved in constructing that prototype. And so I believe that they are scaling up operations to construct antennas for all of the 200 SKA1 mid dishes. As to how they physically will be transported, I don't know. These are very sensitive pieces of electronic equipment, so they obviously have to be transported with care.
Yeah. So our next question is from MCTP, and that says, with so much data per second, will you also get images very quickly? How long will it take to process all that data and get the images out?
So SKA is a bit different from most radio telescopes. So with most radio telescopes, we collect data in some form that is not really very easily understandable as an image, and then some days, weeks or months later, we process it on big computers and then make the images that we are familiar with to go and do science. With SKA, the data will be arriving at such a rate that actually storing the raw data long term will not be possible. So SKA will actually be making images on the fly in real time. Believe it or not, though that takes a huge amount of compute capacity, the trade-off is that you need less disk space in order to do that. So by building a supercomputer at each site, SKA will actually be imaging the sky pretty much in real time.
Wow, okay. Our next question is from Anders Karl, and that says, a bit of a fringe question, but which companies are involved in the production? So I assume that's which Swedish companies do you know are involved in the band 1 receiver?
I should know this, and I regret to say that I didn't actually take note of that information, but if you go to the SKA website, at the top there are 15 flags representing the 15 member states, and if you click on the Swedish flag, I believe that will have more information about the specific companies that are involved. So I hope that non-answer at least points you in the proper direction.
Okay, great. And a final question from Miguel Martinez Durantes that says, if optical telescopes have CCDs as detectors, what do radio telescopes use as their detectors?
It's a very simple and a very complicated question to answer. So in effect, it's similar technology to what you would have in a television aerial. So it's effectively receiver circuits that collect radio waves. They're focused to a point, and then you use amplifiers to amplify that signal. These signals are then fed into a computer, and then the signals are combined digitally to create the data that we use to make radio images. So it's kind of very similar to the technology that you would use, as I say, in a TV or domestic radio or even your cell phone, but it's just very, very high tech and very well engineered to have as little noise as possible and as faithfully recreate the radio waves as they appear.
Okay, great. Thanks so much for answering all those questions. So I don't think we have any more questions from the audience, but feel free to keep commenting and talking to us in the chat if you are watching. I had a final question actually for both of our speakers, if that's all right. So you've both spoken about telescopes to us, and you've obviously gone through some of the science that we hope to get out, but I just wanted to know from each of you, what is the one thing you're most excited about finding out using each of the telescopes you mentioned tonight? So Alistair, seeing as you've just given your talk, what's the thing you're most excited or interested in finding out about using the SKA?
Yeah, sure. So as an astronomer, so my work is on distant galaxies. So I'm very interested in getting the highest resolution, most sensitive images of distant galaxies that we've ever seen in the radio, because this will give crucial information about how stars form, how black holes form and evolve with their host galaxies. Visible light telescopes have been hugely productive, and X-ray and infrared telescopes have been hugely productive at adding pieces to this jigsaw puzzle. But really, radio telescopes have traditionally not been able to join the party on these questions in the very distant universe. So I'm interested very much in radio waves and how SKA will fill the final pieces of that puzzle as to how distant galaxies evolve. But as a non-astronomer, as a human being, I have to say that I find the prospect of detecting ET is super exciting. Given how much radio emission we produce on Earth, as I say, if any alien civilization within several tens of light years is as technologically advanced as we are, or even, dare I say it, more advanced, SKA does stand a chance of detecting them, and I think that's just super cool.
Yeah, I have to say I would be very excited too if the results came out from SKA about ET or something like that. Just as a human being, that would be extraordinary. So Miriam, I also wanted to throw this question over to you again about eROSITA. Is there a specific result or part of science or astrophysics that you're excited to find out more about using that telescope?
Two things. Well, first of all, like the pink elephants, something that we don't expect, and suddenly Rosita got it. What? I don't know exactly. Could be from exotic agents or one super weird galaxy cluster, some new binary stars, I don't know. But the other, and that is more related to the things that I've been doing, is to detect as many as possible galaxy clusters, which with having a huge sample will give us some light, hopefully, to understand the theory of how the universe works, like, maybe some light on the dark matter, dark energy. So that's one of the goals of eROSITA, and that will be my main take on that.
Okay, great. I want to say thank you again to both of our amazing speakers for today's really interesting talks on two very different parts of astrophysics, the very different parts of the electromagnetic spectrum, and worth us remembering that there's so much more to see in space than we can see with our own eyes, and how we can use these telescopes to do that. So we're now going to take another 5-minute break for everybody at home and for ourselves here. So again, feel free to take a bathroom break, go get a drink. And after this, we will be back with Kiana to guide you through our quiz for this evening. So see you all in a bit. Okay, and we are back. So just to give you all a bit of information about the quiz, we do have a delay between us and the actual live stream, but there will be a link in the chat for the Google form, and Kiana will walk you through the quiz, and then we'll give you a couple of minutes to finish filling it out, and then we'll talk you through the answers and announce the winners. So I'm now going to hand over to Kiana, who will talk you through our quiz for this evening. Kiana, you're muted, so great.
Yep, good. Okay, cool. So everybody should be seeing my screen. So the way this is going to work, I'm going to turn on responses. So if you have already clicked on that link, I'm not sure if it was posted before or after I unclicked that. You might need to refresh your page if it says that the quiz isn't active. So the way we're going to do this is I'm going to lead you through the quiz. I'm going to read out the questions for you, and then at the end, I'm going to give you guys 5 minutes to just work through that by yourself if you didn't want to follow along with me, or if you are thinking really hard about a question. So make sure you have your thinking caps on for this. The first thing you need to fill in is just your team name. So I'm just going to fill this out because there's a second page that I need to click through to. And if you have astronomers on your team, I am an astronomer. So I'm going to click yes. If you don't, obviously click no. There's 2 sections to this. The first is a science related question, and then the second is a surprise related section, and you will see what it is when we get there. So the first question on the quiz tonight is, which of the following pictures of the sky is what E. Rosita sees? So if you are paying attention to the talks tonight, you should recognize one of these 4 images. And the second question is, what kind of light will E. Rosita see in? The answers are infrared, X-ray, UV, ultraviolet, or radio light. Again, thinking caps on. Let's go back to what we were talking about previously. You should have an answer. And question 3 is a simple true or false question. Can we use the SKA to indirectly detect gravitational waves? Obviously, yes or no. Question 4, where is E. Rosita located physically? Is it somewhere between the Earth and the Moon? Is it between the Earth and Venus? Is it between the Earth and Mars, or between Mars and Jupiter? Question 5 is, what are the main astronomical objects that E. Rosita is targeting? And the answers here are galaxy clusters, star-forming regions, X-ray point sources, supernova remnants, or all of the above. So if you look at that picture above, that should give you some clue as to what the answer to that question is. Question 6 is, the SKA will look like which of the following images? And here I show 4 different arrays. I think most of these were shown in the talk. So again, picture memory would help here, but I don't have that. Question 7 is, which of the following about E. Rosita or SKA is wrong? The first is E. Rosita on board of a satellite? The second is, both E. Rosita and the SKA will allow astronomers to study galaxy clusters. The third is, within the same amount of time, the SKA will be able to map a larger region of the sky than the JVLA, that's the VLA, the Very Large Array, that Alistair mentioned in the movie Contact in the USA. And the fourth is, the SKA will provide the largest baseline possible on Earth. Question 8 is, data collected by the SKA in a 24-hour period would need blank years to play back on an iPod. The first is 1,000 months. The second is 2 million years, big jump. The third is 100 years, or the fourth is 100 million years. So those are some big scales that we're talking there. The question 9 is a true or false question. Is the Milky Way part of a galaxy cluster? Obviously, this is just a true or false question. Question 10 is, the SKA will use enough fiber or optical fiber to wrap blank times around the Earth. Is it 1, 3, 2, or 5 times? Question 11 is, the SKA cannot be used to detect transit by exoplanets. And this is just another true or false question. And you can see we're trying to trip you up with how we have you select true or false. If it's a drop-down menu or select. Question 12 is, the dishes of the SKA will produce blank times the current global internet traffic. Is it 100 times, 50 times, 10 times, or 5 times? And question 13 is, which of the following statements is correct? It is not possible to detect star formation rates in galaxies located very far away. X-ray observations cannot probe young protostars, or galaxy clusters are only composed of galaxies like our Milky Way, as in spiral galaxies, or is it none of the above? Question 14 is, the SKA central computer will have the processing power of about blank PCs. Is that 100 million PCs, 1,000 PCs, 50 million PCs, or 1 billion PCs? Question 15 is, which of the following about space-based telescopes is correct? Is it that space-based telescopes can be part of very long baseline observations? Space-based telescopes will be able to look further into space than ground-based telescopes? Space-based telescopes, oh, that's a tongue twister, normally have higher resolution than ground-based telescopes, or that Sweden has never manufactured a space-based telescope. Jesus, try saying that 5 times fast. Telescope before. Question 16 is, how close is the closest galaxy cluster to the Milky Way? Is it about 1 light year, 10 million light years, 16 million light years, or 33 million light years? So once you've filled all of those in, you can click next and move on to the second question section, which is about SKA music. And question 17 is, where did ska, that's what it's, how you pronounce it, music originate? Is it Jamaica, the Bahamas, New Orleans, or the Dominican Republic? And question 18 is, which of the following is a United Kingdom-based ska band from the 1980s? And question 19 is, which of the following is I want to say SKA, ska band from Gothenburg? So once you have filled out all of those questions, then just submit your answers, and we will be announcing or going through the answers in 5 minutes. So I'm going to let everybody have 5 minutes to just put your thinking cap on, really think about these questions hard, and then we will come back and I will show you guys the responses. All right, guys, 2-minute warning. So 2 more minutes. So make sure that if you're just starting the quiz, we're going to be going over that in at 9:18. That's when I'm going to be closing the submission window. So make sure if you want to be in on the quiz, please make sure that you click that submit button by 9:18. All right, everyone, I am about to close this poll, so make sure if you have clicked in, we have 10 responses. Anybody about to click? Maybe, maybe? No. Okay, we are done accepting responses. So it looks like, if this loads. Okay, our winner is Team Burrito. Whoever Team Burrito is, good job. And then our follow-up, I guess, so we have our two categories, those with astronomers and those without astronomers. So the yeses, we've got a 12. Yep, so I guess Sid. So I'm assuming that's Andrew. Good job. So if whoever Team Burrito and Andrew, if you want to send us an email with your details, whoever Team Burrito is specifically, so we can get in contact with you. We have like little prizes that we give out for these quizzes. So I'm gonna quickly go through the correct answers to this quiz wherever I can find them somewhere. Okay, so we are going to, that's not an answer. 50-50, lovely. So the first question was, which of the following pictures does eRosita see? Okay, everybody got that, so I'm not gonna go through it. And same with the type of light, X-rays. Good job, you guys were paying attention. Can we use the SKA to indirectly detect gravitational waves? The answer to this is yes. Alistair had a slide in his picture, in his talk that showed this. eRosita is located between the Earth and Mars. This is where the Lagrange point was that was previously mentioned. What are the main astronomical objects that eRosita targets? And that is all of the above, I think, in this image. If we scroll down, so we can see like clusters, superclusters, a pulsar, a nebula, all of our Large Magellanic Cloud. So we see all of these objects with this telescope. Oh, lovely. Now I have to scroll all the way back down again. Okay. The SKA will look like which of the following images, and that is array 1. Oh my gosh. Okay, last time I'm switching back and forth, guys. So that's what this one is. This is this is ALMA. This one is the VLA, and then this one is Meerkat, which is Australia, South Africa. I don't remember. One of the two. You can Google it. Yes. Okay. Question 7. Which of the following about eRosita or the SKA is wrong? And that is that SKA will provide the largest baseline possible on Earth. Question 8, data collected by the SKA in a 24-hour period would need 2 million years to play back on an iPod. As Alistair mentioned, it is a lot of data. True or false, the Milky Way is part of a galaxy cluster. This is false. Question 10, the SKA will use enough optical fiber to wrap around the Earth 2 times. Question 11, the SKA cannot be used to detect transit by exoplanets. That is false. Question 12 is the dishes of the SKA will produce 10 times the global current internet traffic. Question 13, which of the following statements is correct? And none of the above were correct. So it's not, this one is the only one that people apparently clicked on. So it's not that they can, that it can be used to probe young protostars rather. The SKA central computer will have the processing power of about 100 million PCs. And which of the following about space-based telescopes is correct? And it was the first one, which only one person got right, that's sad, which is space-based telescopes can be part of very long baseline observations. And question 16 is how close is the closest galaxy cluster to the Milky Way? And that is about 10 million light years. Okay, so now on to the completely unrelated ska music, and that is where did ska music originate? Jamaica, it's kind of related to reggae. Question 18 is which of the following is a UK-based ska band from the 1980s? And I'm very impressed that anyone got this because I Googled specifically ska bands from the 1980s in the UK and I knew none of them. Well, I guess I knew Sublime, but that's not a UK-based band. But on that topic, Sublime, Lana Del Rey covered one of their songs. And if you want to watch a really weird YouTube video, I recommend you look up that. And question 19 is which of the following bands is a ska band from Gothenburg? And that is the USCB All-Stars. And I don't know who got that, but good job. And that is it from me for the quiz. So I'm going to turn it over to Holly to say goodnight and goodbye to you all. Thank you so much for participating.
Great. Yep. Thank you to everybody who has joined us today for our talks and everything. Thanks to the speakers and everyone's been helping out. So just to let you know that our next talks will be going ahead hopefully in early December. So we're just finalizing speakers. And then if you keep an eye on our Facebook and Twitter pages, we'll be sure to release more details then when we know who our speakers and our talks are going to be. So thank you to everybody for watching, and I hope you enjoy the rest of your evening and the rest of the week. Thank you.